Okay, hello everyone. I welcomes to all in our lecture series on mathematical physics, that is your core paper 8, belongs to 4th semester B.sc physics honors syllabus CBCS model. In last class we have been discussed this question, that is your question number 12, and question number 13, this one. In detail we have been discussed. Okay, and I told this class we are going to discuss the revision of Lorentz series, that what we have been discussed yet, that we are going to just revise, and some basic questions on the Lorentz series. Okay, so let's start. Here your Lorentz series starts from here, from the Lorentz theorem. May you remember, here it has been started. This is your so-called Lorentz series. This is your analytic part, this is your principal part, because here z minus z0 to the power n is a positive integer, and here z minus z0 to the power minus means negative integer. So this will be called as your principal part, this is your analytic part. Each and every step we have been discussed, that in how we are going to take the outer circle, inner circle, then how we are going to consider the cross cut by removing this z0 where the function is not analytic. In detail we have been discussed, and we found that the function fz will be f1z plus f2z. F1z is a one, this like this one integral, f2z is another integral. This integral considering c1 circle, outer circle f1, and f2z considering inner circle. In detail we have been discussed, right? By using Cauchy's integral formula we proved the Lorentz series. And here I'm going to show you evaluation of f1z when we don't know. At that time 1 minus z dash minus z written as z dash minus z0 minus z minus z0, because for outer circle, outer to in, if we are going to move, then we have to use this procedure, or this method, or this step we have to follow, that 1 by z dash minus z0 minus z minus z0. Whenever we are going to consider f2z means inner circle, we have to move into out situation. For that 1 by z dash z minus z dash will be written as 1 by z minus z0 minus z dash minus z0. That means whenever we are going to consider out to in situation, at that time the denominator of the function will be written in this format, 1 by z dash minus z0 minus z minus z0. For in to out case we have to write 1 by z minus z0 minus z dash minus z0. Then we have to check that it is matched with original function or not. Then if it is matched, no problem. It is not matched, then we have to multiply minus, then blah blah, that we have been discussed in the numerical. Okay, so these two expressions you have to remember to solve the Lorentz series that we have been discussed in detail. And finally we have been proved analytic part this one, आप principal part this one. ये तो हो गया Lorentz series के बारे में. उसके बाद on the Lorentz series, or by using Lorentz series, we have been solved few numericals. What are the numericals? Here I am going to show you one by one from the beginning itself, from question number 1 itself. I am going to show you first. You just watch. In question number 1 we discussed 1 by z Lorentz series about its singular point, that is your z equal to 0, and Lorentz series of 1 by z minus 1 about its singular point z equal to 1. In detail we have been discussed. Okay, in detail, and we found Lorentz series of a function about its singular point. That means the function itself we can found here. 1 by z is there, and about its singular point 0, the function itself we can found. The Lorentz series of 1 by z about z equal to 0 will be equal to 1 by z, or we can write in this format 1 by z minus z0. But keep in mind that always the series will be, Lorentz series will be in this format, 1 by z minus z0 format. So here z0 is your 0. So 1 by z Lorentz series about z0 equal to 0 will be 1 by z. Likewise, Lorentz series of 1 by z minus 1 about z equal to 1, we found same 1 by z minus 1. Here you can see the z0 is 1, and here finally we found in this format 1 by z minus z0. Z minus z0 means is your 1. In detail we have been discussed. Okay. Likewise, Lorentz series of 1 by z minus 3 about its singular point 3 will be 1 by z minus z0. Here z about z equal to 3 means this is your z0. So the answer will be 1 by z minus z0. Right. Then we have been discussed Lorentz series of 1 by z into z minus 1. In detail, we have been discussed that question, and we found Lorentz series of 1 by z into z minus 1 will be this much, okay, or this much. Here we written this term first and this term second. We found this one, the Lorentz series of this one, 1 by z into z minus 1 about z0 equal to 1. Question number 3, we have been discussed 1 by z minus 3 the function. Lorentz series about z0 equal to 5. In detail, we have been discussed here. Z0 equal to 5 is not the singular point of the function. That means indirectly question asks that we have to find out the Taylor series. So f2z will be 0 because c2 could not be considered for this case. So how we are going to do in detail we have been discussed. And question number 6, 1 by 5 minus z about z equal to 7. This is also z equal to 7 is not the singular point. That means question asked that we have to find out the Taylor series about that point. Here, question number 5, 1 by z plus 5 about z equal to 7 or z0 equal to 7. Here, z0 equal to 7 is not the singular point for this function. That means indirectly it is asked that we have to find out the Taylor series. So here, z equal to minus 7 or z0 equal to minus 7 about, we have to find out the Lorentz series of 1 by z plus 5. Here, minus 5 is the singular point. Minus 7 about we have to find out means indirectly it is asked that we have to find out the Taylor series. Each and every step also I explained, and I told that you have to write in your notes systematically. Then question number 7, we discussed or we calculated Lorentz series of 1 by 5 minus z into z plus 5 about z equal to 5. In detail, we have been discussed. Question number 8, Lorentz series of 1 by z minus 2 into z minus 3. In between the annular region z equal to 2 and z equal to 3, in detail we have been discussed. Lorentz series in this region, what it will be for this function, in detail we have been discussed. You go through that and practice for your exam. Question number 9, we have to find out the Lorentz series of 1 by 5 minus z for region z mod greater than 5 means outer region, z mod less than 5 means inner region. In the two different regions, what will be the Lorentz series for this function, we have been evaluated in question number 9. Question number 10, different regions, z mod 3 less than 3, z mod greater than 5, and in between 3 to 5. For this function, Lorentz series will be how much? We have been evaluated. Z mod less than 3 means minus 3 to plus 3 range is the region. And here Z mod greater than 5 means below minus 5, above plus 5. What is the region? Or we can say outer region. And I told that this for region based question, the figure is most important. I'm going to show you here previous question. If we are going to consider this one here. Here it has been given that annular region means z equal to 2, and this can be written in the circular equation as z minus 0 equal to. So 0 is the center, and here z minus 0, 0 is also center. But here for this case radius is 3, for this case radius is 2. So we have to just draw by considering center at O having the radius 3, 1 circle here. Equally spaced interval I have been considered. This is 1, this is your 2, 2, and this is your 3. So 1, 2, 3, minus 1, minus 2, minus 3. So we have to consider 3 is our radius. 1, 2, 3 is our radius. I consider the rounder. 3, by considering 3 is the radius, I draw the circle. Then by considering 2 is the radius, I draw the circle. In between that 2 circle, this is the region, the so-called annular region. Okay, and we have been evaluated the Lorentz series that we discussed in detail. Next question, as I told, question number 9, also I drawn the figure perfectly. I suggested to you, again I am suggesting that you just draw the figure perfectly. This interval you have to take perfectly by considering the scale. Okay, you just consider the scale and take the intervals. Each and every intervals is the equal space. So here 5 is the singular point over here, and z mod greater than 5 means less than minus 5, above plus 5 region, outer region clearly written. For z mod less than 5 means inner region. For outer region, this is the Lorentz series. For inner region, this is the Lorentz series. We have been evaluated in detail. Yes, question number 10 we have been discussed. This is one of the important question. In this question we have been discussed Lorentz series of 1 by z plus 3 into z plus 5 in this region, z mod less than 3, z mod greater than 5, and 3 less than z mod less than 5. So first of all, here for this question we have been considered the partial fraction, and we found this one. So Lorentz series of this one is nothing but Lorentz series of 1 by z plus 3 and 1 by z plus 5. Separately we have to find out the Lorentz series and we have to substitute it over here. If I'm going to consider the first case or first option, that z mod less than 3, that means minus 3 to 3. This is the region we have to consider by considering the mod function. If I'm going to draw this one, this equation as circle, that means z here, this one can be written as z minus 0 mod less than 3. So here z minus something, no, that something is called as the z0 or the center of the circle. So this is the center of the circle which is at z0, and we are going to consider the radius 3, 1 2 3, but the radius should be always less than 3. Just below the 3 the circle is going to be passed, just below the 3, just here below the minus 3 the circle has been passed, and this, after drawing this circle, we found the region where we have to find out the Lorentz series of different functions. So first function is your, for this case, 1 by z plus 3. So considering 1 by z plus 3 for this region, we found this is the Lorentz series, and for z plus 5 we found the Lorentz series is this one. Okay, and by substituting at 1 by z plus 3 minus 1 by z plus 5, and finally the Lorentz series of the given function will be this much, right? Then we have been discussed question number, yes, this is case for z mod less than 3. Then by considering z mod greater than 5, also we found the Lorentz series, this one. This is the expansion form. Then by considering the region in between 3 to 5, in between 3 to 5, here you can see 3 to 5 means, by considering the what circle equation method, this can be written as 3 less than z minus 0 mod less than 5. That means this is represents your center of the circle or the so-called z0. This is the larger circle, smaller circle. By considering z0 at 0, we draw on a circle having the radius is 3, that is your smaller radius, 1 2 3, larger radius is 5. Okay, after that, hence we found the region in where we have to find out the Lorentz series. So this is the annular region where we have to find out the Lorentz series of 1 by z plus 3 and 1 by z plus 5, right? Then we have been determined the LS of 1 by z plus 3. We found this one. Okay, only principal part, there is no analytic part is found for this one. 1 by z plus 5, 1 by z plus 5, in this region we found the Lorentz series is this one. Okay, this one for 1 by z plus 5. Finally the function is 1 by 2 into 1 by z plus 3 minus 1 by z plus 5. So for 1 by z plus 3, the Lorentz series, this one has been substituted, 1 by z plus 5 has been substituted, and finally we got the, this one is the Lorentz series of the given function. Then we have been discussed this question, 7z minus 2 by z cube minus z square minus 2z. For this region, this region, this region, in detail we have been discussed. To determine the range, we consider the mod function. First we done the partial fraction, and we segregated this function as 1 by z plus 2 into 1 by z minus 2 minus 3 into 1 by z plus 1. And here the singular points are 0 plus 2 minus 1, and considering this range or this mathematical range, we found the range is this one, minus 2 to 0. Minus 2 will be lower limit, upper limit is your 0, and minus 1 is the point, only point. Same thing also we found by considering circular equation. I suggest that you go through this video, okay, perfectly. So then we found the Lorentz series of 1 by z, 1 by z minus 2, then 1 by z plus 1 separately. Finally we found the Lorentz series of the given function, this one, or this is the expansion form. Likewise, second I is the range is your 1 less than z plus 1 mod less than 3. If it is so, how we are going to do this? Here you can see. First we have to define the range. Here by two method I defined the range by mod function by considering circular equation. I told that you have to consider the circular equation method to determination of the range. Here you can see by circular equation, here z plus 1 mod has been given, z plus 1 mod. This z plus 1 can be written as z minus of minus 1. This minus 1 is the center of the circle, 3 is the larger radius, this is the smaller radius. By considering these information, we have to consider here, this is a complex plane, 0 1 2 equal interval you have to consider. By scale and rounder you have to use to draw this figure. 0, 1, 2, 3, 4, and so on. Here -1, -2. We got the center is your -1. Here will be the center. Then my 3 is the larger radius, means one interval, another 3, means from here to here is the radius we are going to take. For the larger circle, this will be the circle, and for the smaller circle, radius is 1. This is the center. You have to consider the one interval for the smaller circle, this one. So in between these two circles, we have to consider the region. So this is the region. Then we found the Lorentz series, or we evaluated Lorentz series of 1 by z, 1 by z minus 2, 1 by z plus 1 separately. Here you can see that when we evaluated the Lorentz series of 1 by z plus 1, we found the same value, because here z dash and z0 has been coincided with a same point, that is a -1. As we discussed, if the z0 and z dash means singular point and z0 means about which we have to find out the Lorentz series. Here both are coincided, that means the function itself the Lorentz series of that function. So 1 by z plus 1 is the given function, and 1 by z plus 1 will the Lorentz series of this function, or we can write this one like this: 1 by z minus of -1. This is in the form of what? 1 by z minus z0 form, right? Okay. Then we consider this region, third eye region. We determine the region by two methods. This is the region for z plus 1 greater than 3. Region is your this one, outer region. -1 is the center, and we have to consider this outer region. Lorentz series of 1 by z in this region we determined. Lorentz series of 1 by z minus 2 in this region also we have been determined. Lorentz series of 1 by z plus 1, we found the same, because the Lorentz series of z plus 1 about z0 equal to -1 and z dash -1, because z dash is the singular point of this function. So Lorentz series of 1 by z plus 1 will be 1 by z plus 1, or we can write, as I told, 1 by in the form of z minus z0 minus of -1. This is the in the form of 1 by z minus z0. Okay, so here 1 by z minus of -1 is nothing but 1 by z plus 1. Simply we remember that Lorentz series of 1 by z plus 1, here the point about which we have to find out the Lorentz series and its corresponding singular point coincided, and we found the same. Lorentz series of 1 by z plus 1 will be 1 by z plus 1. So in general, I am going to tell to you, just remember that suppose we have 1 by, previously just we have been discussed that we are going to discuss. Here you can see 1 by 5 minus z is there, suppose, and about z equal to 5 we have to find out the Lorentz series, right? So here you can see that about z equal to 5, that means here z0 is your 5, and z dash means singular point of this function is also 5. So both are coincided with each other, means Lorentz series of 1 by 5 minus z will be 1 by 5 minus z. Okay, but actually in general we have to write in the form of 1 by z minus z0. 1 by z minus z0 means, in which way we can write 1 by z minus z0. Here instead of z0 we have to write 5. So if I am going to write 1 by z minus 5, then this is not matched with this one. Always remember that function itself, its Lorentz series, when we are going to find out the Lorentz series about its singular point. So 1 by 5 minus z Lorentz series will be 1 by 5 minus z, but we have to write in this format. For that, what we have to do? We have to just multiply -1. Here you see -1 I multiplied, means this is nothing but 5 minus z. So Lorentz series of 1 by 5 minus z is nothing but minus of z minus 5, or minus of, in this format, z minus z0 form. It has been automatically written, right? Now I'm going to show you, after this question we have been discussed question number 12, this one about z equal to 0. The question it has been given that about z equal to 0 we have to find out the Lorentz series. So here in this question not given the range. So if it is not given the range, we have to consider three possible regions. In detail we have been discussed in the question number 12. in different regions, what are the Lorentz series that we discussed. Then finally, this is the question number 13, that what is the Lorentz series of this function in this region we haven't discussed. Okay, so these are the questions we have been discussed. Right, now what are the important results we have been found, that I'm going to show you. So as I told, come to the question number 1. Here I'm going to show you that we have been discussed already that, and we know that if Lorentz series, we have to find out its corresponding singular point. The Lorentz series will be itself the function. So 1 by z about z equal to 0, Lorentz series will be 1 by z. So it is written in the form of 1 by z minus z0 form. Likewise 1 by z minus 1 about its singular point z equal to 1, Lorentz series will be same 1 by z minus 1, that is your in the form of 1 by z minus z0. As I told, if it will be written in the form of suppose 1 minus z, what will the Lorentz series? Lorentz series will be minus 1 by z minus 1. If it will be 1 minus z will be there. So same type of question we can found in here in the question number 7. I'm going to show you. In the question number 7, here you can see here 1 by 5 minus z into z minus 5 about z equal 5. We have to find out the Lorentz series. You can see that for this one by 5 minus z, particularly here after by partial fraction we found this one, and we have to find out the Lorentz series of this one by 5 minus z about z0 equal to 0. Here z0 means about this point we have to find out, but singular point of this function also 5. That means both singular point, that means z dash z0 are coincided with each other. So hence 1 by 5 minus z Lorentz series will be equal to 1 by 5 minus z, right? So this can be written as, here you can see 1 by 5 minus z Lorentz series will be same 1 by 5 minus z, or we can write, or minus 1 by z minus 5. This one by 5 minus z can be written as 1 by 5 1 minus 1 by z minus 5. Lorentz series will be minus 1 by same z minus 5, because it is written in the form of z minus z0. Here 5 is the z0, no, z minus z0 to the power minus 1 form. Okay, you just remember, as I told, if one function is there and we have to find out the Lorentz series about its singular point, the function itself it's a Lorentz series, but we should write in this format, z minus z0 format. So for this type of case 1 by 5 minus z, it will be, answer will be, Lorentz series will be minus of 1 by z minus 5 or z minus z0, right? And another one interesting result I'm going to show you. Here you can see, which will be required to reduce the step. How? I'm going to show you. You just go to the question number 2. Here we found the Lorentz series of 1 by z into z minus 1. We about z0 equal to 1. Finally, what we found? We found this one. Okay, this one, the Lorentz series of 1 by z into z minus 1 about z0 equal to 1. We determined the Lorentz series of 1 by z minus 1 about z0 equal to 1. It will be itself 1 by z Lorentz series about z0 equal to 1. This one we just substituted and we found this is the final Lorentz series of this function, right? Here in this case, what we done, we separately found the Lorentz series of 1 by z, 1 by z minus 1 and 1 by z. Separately we have been determined, and then we have been substituted. Okay, I'm going to show you. Wait, here you can see. Carefully observe and watch. 1 by this one, z into z minus 1, Lorentz series about z equal to 1 will be this one. If I'm going to write in the expansion form, here you can see this value will be 1 by z minus 1 minus, this will be, first term will be n, if I will put n equal to 0, this will be 1 minus z minus 1 by substituting n equal to 1. Here minus 1 to the 1 will be minus z minus 1 to the 1, then plus, because minus 1 to the 2 will be plus 1, z minus 1 to the power 2, then minus z minus 1 to the power 1 to the power 3, plus so on, right? Plus so on. Here you can see it can be, here 1 by z minus 1. You just multiply this minus with each term. This will be minus 1 plus z minus 1 minus z minus 1 whole square plus z minus 1 whole cube, then minus and so on. So this will be the series. Okay. So here, how we found this Lorentz series? By first we determined the Lorentz series of 1 by z, then 1 by z minus 1 separately, and we found this one. So without doing so, we can omit many steps for this question. How it is? Carefully you have to watch. This is most important. Okay, I'm going to explain again. For this question, what we done? We done first the partial fraction. By partial fraction, we found the two functions. Separately, we found the Lorentz series of this one, then substituted, and we got the Lorentz series. This is the expansion form. So here, in the question, it has been asked that we have to find out the Lorentz series of this one about z0 equal to 1. So without doing partial fraction, particularly this type of question, without doing partial fraction, we can solve this question with few steps. How? Here you can see, in this function, here 1 by z one function is there, 1 by z minus 1 is function is there. For which function z0 equal to 1 is the singular point? For this function, right? For 1 by z minus 1, here two functions are there. For which function z0 equal to 1 is the singular point? For this function 1 by z minus 1, for 1 by z minus 1, z0 equal to 1 is the singular point, right? What we have to do here, you just take outside 1 by 1 minus z, you take in, and then you just write the Lorentz series or Taylor series of 1 by z. Then we have to find out the LS or the so-called TS of 1 by z about z0 equal to 1. What I done here? Here, as we know that the Lorentz series of this function about its singular point itself, then I written first. Okay, that means here this function is written in this form, no, 1 by z into 1 by z minus 1. We have to find out the Lorentz series about z0 equal to 1, no. So 1 by z minus 1 Lorentz series about its singular point is itself 1 by z minus 1. I have been written first. Then 1 by z Lorentz series about z0 equal to 1 is nothing but it is Taylor series. So Taylor series of this one we have to write. So here 1 by z minus 1 written. The Taylor series of 1 by z already we found. That means here we have been evaluated step by step. Here Lorentz series of 1 by z about z0 equal to 1 means it is asked that we have to find out the Taylor series, or by considering this form separately, that f1z into out to in, you can consider those procedures. And what we found, the Taylor series or Lorentz series of 1 by z about z0 equal to 1, we found this one, right? How much? This one. Okay, I'm going to write that one. That is your summation over n equal to 0 to infinity minus 1 to the n z minus 1 to the power n. You just open this bracket, or you just write in the expansion form and multiply 1 by z minus 1. We can found the same series. I'm going to show you 1 by z minus 1. Here this will be 1 minus z minus 1 plus z minus 1 whole square minus z minus 1 whole cube plus z minus 1 to the power 4 minus, so right. I'm going to multiply 1 by z minus 1. What I am going to get here, 1 by z minus 1 minus 1 by z minus 1 multiplied with this term minus 1 by z minus 1 multiplied with this one plus z plus 1 z minus 1 multiplied with this one minus z minus 1 whole square, 1 by z minus 1 multiplied with this one plus z minus 1 whole cube minus, so on. You just match this one and this one is exactly matched or not, this one and this one. Here 1 by z minus 1 minus 1 plus z minus 1 minus 1 plus z minus 1 minus z minus 1 square plus z minus 1, so exactly matched. So here by this method we removed or escaped so many steps. So many steps means we no need to find out these things itself. But Lorentz series of 1 by z minus 1, no need to find out, and no need to do the partial fraction itself. Got it? Okay. On the base of that, if I'm going to consider, similarly, if I'm going to consider question number 7 here. Question number 7 about z equal 5, we need to find out the Lorentz series, right? Finally, what we found? We found this one. Lorentz series of 1 by 5 minus z into 1 by z plus 5 about z0 equal 5, this much. Okay, if I'm going to do this question by this method without doing the partial fraction, if I'm going to do this by this method, also we can get the same answer. I'm going to do for you. Carefully you have to watch. See, these are the method that you have to remember. What we have been done previously, we done by considering the traditional method. Okay, here I'm going to write the Lorentz series. You can write this one, or you can write this one also, no problem. I'm going to consider this one, or this one you can consider, no problem. Here, Lorentz series of 1 by 5 minus z into z plus 5. See, this is your revision class. Okay, revision class. So 1 by 5 minus z into z plus 5 about z0 equal to 5, we found 1 by 100 summation over n equal to 0 to infinity minus 1 to the power n z minus 5 to the power n by 10 to the power n, then plus minus of 1 by 10 z minus 5 to the power minus 1, or we can write 1 by, this is z minus 5 to the minus 1, or 1 by z minus 5. This one, this much we found. I'm going to write it in the expansion form. Here, this will be 1 by 100 into 1 plus 1 minus n equal to 0. N equal to 1 means this will be minus z minus 5 by 10. Z minus 5 by 10. If n equal to 1, 1. So z minus 5 by 10 plus z minus 5 by 10 to the power 2 minus z minus 5 by 10 to the power 3 plus so on, plus this will be plus, this minus is there. Okay, so this will be minus 1 by 10 into 1 by z minus 5, right? This is the value we found, the Lorentz series of this one, by considering this method, that considering C1, C2, by traditional method you can say. Now I'm going to consider this method, that here it has been given that we have to find out 5 minus z, z plus 5, Lorentz series about z equal to 5, right? What we have to do? What we have to do here? Here no need to do the partial fraction. Here you just consider two functions are there multiplied with each other, 1 by z plus 5, 1 by 5 minus z. So z0 equal to 0, whose singular point, z plus 5 or 5 minus z? 5 minus z. So 1 by 5 minus z, if I'm going to consider the function, its singular point is your 5, right? So the Lorentz series of this one, 1 by 5 minus z, will be nothing but itself 1 by 5 minus z, but it has to be written in this format, z minus 5. So it will be minus of z minus 5. Got it? So the Lorentz series of 1 by 5 minus z, first I am going to write this one, minus 1 by z minus 5. In एक काम खत्म, one work has been over. Then we have to find out the Lorentz series of LS, or the so-called TS, of 1 by z plus 5 about z0 equal to 5. What we have been already determined here, 1 by z plus 5, 1 by z plus 5 Lorentz series is this one. We found in detail, and also you have to obey this procedure to find the Lorentz series or Taylor series of 1 by z plus 5, or for the Taylor series you can consider the what, the so-called that is, a0 into z minus z0 to the n, an, for an equal to n equal to 1 by n factorial, dn fz by dzn at z equal to z0, and Taylor series of that function fz equal to this one, summation over n equal to 0 to infinity an into z minus z0 to the power n. So finding an, we can find the Taylor series by this method, or I suggest that while you are going to find out the numbers of derivative, here this is the easy method to find the Lorentz series or Taylor series of a function about any point except its singular point. So 1 by 5 minus 5 plus is z is there. We have to find out the Lorentz series about z0 equal 5, which is not its singular point. So that means indirectly it adds the Taylor series. So this method you just adapt to find its series. And what is the value we found here? That I am going to write here, this value. So here we found 1 by z minus 5, right? 1 by minus 1 by z minus 5 we found, and then this one Lorentz series of 1 by z plus 5 about z0 equal 5. This one I have to write 1 by 10, 1 by 10 summation over n equal to 0 to infinity, here n equal to 0 to infinity, n equal to 0 to infinity minus 1 to the power n, minus 1 to the power n into z minus 5 by 10 to the power n. Okay, same thing also it has been written over here. I haven't written. Now I'm going to just expand it. Then after multiplication, we can found this series. You just check. Minus 1 by z minus 5. Keep it. This will be 1 by 10 is there. Then you just expand this series. This will be 1 minus z minus 5 by 10. Then plus z minus 5 by 10 to the power 2, because n equal to 2. 0, 1, 2. Then minus z minus 5 by 10 to the power 3. Then plus z minus 5 by 10 to the power 4. Then minus, and so on. Okay. So here minus 1 by z minus 5. This one. If I'm going to multiply 10, then it will be 1 by 10 minus z minus 5 by 10 to the power 2 plus here z minus 5 square. This 10 is multiplied, so this will be 10 to the power 3 minus z minus 5 to the power 3. Here 10 to the power 3 will be, and this 10 is multiplied means 10 to the power 4. Then plus z minus 5 to the power 4, 10 to the power 5, minus, and so on. Right? Now I'm going to multiply this one with each term. What I'm going to found minus 1 by 10 into 1 by z minus 5. This one multiplied with this one. Then minus this one, minus plus z minus 5, z minus 5 got cancelled. We can get 1 by 100. 1 by 100. Then this term multiplied with this term, z minus 5, and here z minus 5 square got cancelled, and this is minus, this is plus, minus z minus 5 divided by here 10 to the power 3, right? Then minus, this is minus, plus z minus 5, 1 z minus 5 we got cancelled, and we found z minus 5 to the power 2 divided by 10 to the power 4. Then next term will be minus z minus 5 to the power 3 by 10 to the power 5. Then so on, right? Okay. Now you just compare this and this. This and this you just compare. Both are same. How? Here is the last term, minus 1 by 10 into 1 by z minus 5. Here it is came in the first term. Got it? Okay. Now here, if I'm going to multiply 1 by 100 with each term, then this will be what? This will 1 by 100 here, plus 1 by 100 term I got. 1 by 100 minus z minus 5 by 100 into 10. 100 into 10 means what? 10 to the power 3. Z minus 5 by 10 to the power 3. Here z minus 5 to the power 2 by here 10 to the power 2. Here 10 to the power 2 multiplied means 10 to the power 4. Z minus 5 to the power 2 by 10 to the power 4. Plus here also plus 1 by 100 multiplied with this one. That means here 10 to the 2, here 10 to the 3, then 10 to the 5 minus z minus 5 to the 3 by 10 to the 5. We got, and we got the same series. So here what we got the profit. हमको लाभ क्या मिला इसमें, इस प्रोसीजर में? We no need to do the partial fraction this way. Suppose 2 mark question has been asked, suppose this is a 2 mark question, no need to do the partial fraction. इधर हमको देखना है कहाँ पे, about which point we have to find out the Lorentz series, about z equal 5. So z equal 5 is the singular point of this function. इसका Lorentz series हो जाएगा कितना, -1/z-5, then 1/z+5 के Lorentz series about z equal 5 निकाल दो, उसमें मल्टीप्लाई कर दो, हो गया बस, और कुछ नहीं चाहिए. 2-3 स्टेप में काम खत्म. ठीक है, विदिन 2 and 3 स्टेप योर वर्क हैज बीन ओवर. ओके, नाउ ऑन द बेस ऑफ this concept I am going to solve a numerical for you. You just watch. Okay, I told that this is a revision class, and we are going to do some numericals. Okay, so here we just revised somewhat what we have been previously discussed about the Lorentz series. Now we are going to go for the basic questions, some basic questions, that means 2 to 3 mark questions. Okay, 2 to 3 mark questions I am going to discuss over here. 2 mark, 1.5 mark, like that. Here the first question is, yes, before we are going to discuss the basic questions, I forgot one thing that we have been discussed, that here I am going to show you. I forgot to say that one. Suppose we are going to consider this one, this question number 11. The range has been given that 0 to 1, 0 less than z plus 1 mod less than 1. So how we are going to do this numerical? This question also can be done by another method. What is that? Here I discussed in the previous class itself, that suppose we are going to consider this range 1 less than z plus 1 mod less than 3. Here z plus 1 can be considered as t, then we have to consider the range as this one. 0 will be the center, 3 is the larger radius, smaller radius, and here we are going to find out the t0 value will be 0 corresponding t dash. That means we have to find out the Lorentz series of 1 by z, means here z plus 1 equal to t, means z equal to 1 by t. So 1 by t minus 1, 1 by t minus 1 means corresponding singular point or t dash will be 1, and we done the numerical and we found the same answer. Here I'm going to show you 1 by z in that region. In that class I shown you. Okay, 1 by z. Here this is the question. 1 less than z plus 1 less than 3, Lorentz series of 1 by z, we found this one. 1 by z plus 1 summation over n equal to 0 to infinity 1 by z plus 1 n to the power n, and in this method by considering t also we found the same. By considering 1 by z minus 2 function, 1 by z minus 2 in this range, we found this one, Lorentz series, and by considering t also we found same. I suggested at that time that either one procedure you can consider, but here by considering t you have to do 2 to 3 extra step. That means first you have to consider z plus 1 t, then you have to reconsider, you have to re-substitute t equal to z plus 1. So 1 or 2 step extra you have to do by this method. I suggested that you have to do by this method. Now we are going to go for some simple questions on or basic questions on Lorentz series. So here is the first question, belongs to basic questions on Lorentz series. Question number 14. Last question number was your question number 13. Okay, here you can see we have to find out the Lorentz series of the function 1 by z square plus 1 about its singular points. So here given function is 1 by z square plus 1. So this z square plus 1 can be written as z plus I into z minus I. So it has two singular points, I and minus I. So first we are going to find out the Lorentz series about z0 equal to I. So here 1 by z plus I into z minus I. Here it has two functions multiplied with each other. One is your 1 by z minus I, another is your 1 by z plus I. Among these two functions, which have the singular point is belongs to I. Here we have to find out the Lorentz series about its singular points. So if I am going to consider the first singular point I, about which we have to find out the Lorentz series, you just say among these two functions I is belongs to whose singular point? This one. For this function 1 by z minus I is the singular point of this function. So just now we have been discussed that If it is so, then the Lorentz series of this one we have to write as such. The Lorentz series of this one about its singular point is your 1 by z minus I written, and then we have to find out the Lorentz series or the so-called Taylor series of 1 by z plus I about z0 equal to I. Here for this one by, now we are going to go for finding the ls ls of 1 by z plus I, ls of 1 by z plus I. So for this z plus I, singular point is your minus I, will be considered as your z dash, and z0 is given that I. So now we are going to draw the figure. Here z0 is I, means here in the complex plane this is the I. So as the Taylor series we are trying to find out, that means from this I we have this function is spread in all the way, and it will be interacted with its singular point, that is your minus I, and it is stopped the spreading. So this is the region. That means, see, this is the tricks, spreading the function, etc. What the language I am using, this is one tricks you can say. So from I, this is the point where about which we have to find out the Lorentz series. So if the function is going to spread, this function 1 by z plus I, it will interact its singular point I, and it is stopped. So here at minus I is the singular point. So at minus I, you just stand over here and move into this region. That means you are moving out to in. So this is the situation, is out to in. So out to in means 1 by z plus I will be written as 1 by z dash minus z0 minus z minus z0. So here you consider 1 by z dash is your minus I, z0 is your I, minus I minus z minus z0 is your I. Now you just compare this one and this original function is same or not. Here you can see this is 2I minus plus I. So we can found minus I minus z, but we have 1 by z plus I. That means we have to multiply another minus. So 1 by z plus I, here minus 1. Here this is I minus I minus I. 2I minus z minus I. I told that you should not remove this bracket. First term is your 2I taken outside. That means taken common from these two terms. We can found minus 2I whole into 1 plus z minus I by 2I. Here you can see z minus I by 2I will be always less than 1 in this region. You can check. So 1 by 1 plus z minus I by 2I series will be how much? Here summation over minus 1 to the power n, summation over minus 1 to the n, summation from n equal to 0 to infinity minus 1 to the n z minus I by 2I to the power n. Because I told that you have to always remember this one, that if we have this situation that 1 by 1 minus x Taylor series about z equal to 0, then the value will be summation of n equal to 0 to infinity x to the power n, plus x means minus 1 to the power n, x to the power n. So here instead of x, what is there? Z plus I by 2I. So this will be minus 1 to the power n. Summation is there, n equal to 0 to infinity z minus I by 2I to the power n. Here minus minus got cancelled, 1 by 2I is there, 1 by 2I. So finally Lorentz series of the function, this one will be how much? Already we written this much already, 1 by z minus I, 1 by z minus I into Lorentz series or the so-called Taylor series about z0 equal to I of this function 1 by z plus I. We found this one, we just written. So this is the answer, right? So here no need to do the partial fraction for this function. Likewise about z0 equal to minus I, if we want to find out how it will be, here you can see 1 by z plus I into z minus I is the function given. So here you can see the two functions are there, 1 by z plus I, 1 by z minus I. Among these two functions, z0 equal to minus I is the singular point for whom? For this one or this one? For this one. For 1 by z plus I, singular point is your minus I. So what will be the Lorentz series of 1 by z plus I? Itself 1 by z plus I. Or you can say 1 by z minus of minus I. Same thing, 1 by z plus I written into Lorentz series of 1 by z minus I about z0 equal to minus I, we have to find out. For that, z0 is your minus I. From minus I, the function is going to be spread, and where it has to be interact, it will be interact with its singular point is I, and that at that point the spreading will be stopped. That means we found this region. So in this region we have to find out the Lorentz series of this function 1 by z minus I. So stand over here, this is the singular point of this function 1 by z minus I. About z0 equal to minus I, we have to find out. stand at its z dash. I told that z dash always the singular point of that function. So here z dash, here z dash is your I. If you will stand over here and you are moving inside this region, that means out to in situation, out to in. Now 1 by z minus I will be written as 1 by z dash minus z0 minus z minus z0. Z dash is your I, z0 is your minus I, so minus minus plus I minus z. Z0 is your minus I, means minus minus plus. Now you just compare 1 by this one is equal to this one. Compare 1 by this will be 2I minus z plus I. That means 2I minus I. That means I minus z. But we have z minus I. 1 by z minus I is the original function. So what we have to do? We have to just multiply this one. See, before you have to watch this lecture, you just go through the previous videos, because here I am doing these questions with fast manner. Means here why it will be z dash minus z0, why minus z minus z0, what is out to in, everything in detail we haven't discussed in our previous videos. Yeah, here I'm doing with the fast manner. Okay, so here what we got, minus 1 is there, I 2I. I told that z plus I means bracket you should not be open, z plus I will be there. I'm going to zoom somewhat. Okay, so 2I the first term taken outside, so it will be 1 minus z plus I by 2I. So here minus 1 by 2I will be there. Here 1 by 1 minus z plus I by 2I will be how much? Summation over series will be summation over n equal 0 to infinity. This much z plus I by 2I to the power n, because 1 by 1 minus x will be equal to summation over n equal 0 to infinity x to the power n. I suggest again that you should remember these four things, that your this one, if 1 by 1 minus x situation means we have to use n equal 0 to infinity x to the power n. 1 by 1 plus situation will be there, means summation over 0 to infinity, but minus 1 to the power n, same x to the power n. And here x always will be less than 1 in that particular region. And if we are going to consider out to in, we have to write the function will be in the form of 1 by z dash minus z0 minus z minus z0. Into out means 1 by z minus z0 minus z dash minus z0. We have to write the original function. Then we can found easily the Lorentz series of that corresponding function. Now here 1 by 2 minus I, this much we found. Then finally the Lorentz series of this given function, that means 1 by z plus I into 1 by z minus I will be already 1 by z minus I, z plus I Lorentz series is nothing but 1 by z plus I written over here, and the Lorentz series of 1 by z minus I about z0 equal to minus I, or you can say that the Taylor series of 1 by z minus I about z0 equal to minus I will be this much. Here I written. So the Lorentz series of this one about another singular point will be this one. Okay, here this Taylor series or this series can also be found by this method. I told no that one, by considering Taylor series method, that is your fz equal to summation over a n equal to 0 to infinity a n z minus z0 to the power n, where a n is your this one 1 by n factorial nth derivative of fz by nth derivative of fz with respect to z at z equal to z0, and we can get the same series itself. Okay, but I suggest that for this type of question you go through this procedure. So here we what we found that we are not going to go through the partial fraction. We done this question directly. Now we are going to do another question. Here you can see, suppose in the question it is asked that find the LS of 1 by z into z minus 1. This much it is asked. So if it is so, then we have to find out the Lorentz series of this function about its singular points. Okay, here if the question asked this much only, we have to find out the Lorentz series about both of its singular points. That means we have to consider all the singular points. So solution is here, given function is your fz equal to 1 by z into z minus 1. From this function clearly it can be observed that the singular points are z equal to 0 and z equal to 1, right? So here if I will put 0, then the function not to be analytic. If I will put 1 over here, the function not to be analytic. So these are the two singular points. Now we are going to find out the Lorentz series of this one about this one and this one. First we have to consider about z equal to 0 about z equal to 0. Okay, so here 1 by z into z minus 1 is there. So what we have to write this one? First we have to write the two functions multiplied with each other. 1 by z into 1 by z minus 1. You just watch. 0 is the singular point for whom? For this one. Z equal 0 is the singular point for this function. Okay. Hence, if we are trying to find out the Lorentz series about z equal 0, then first the Lorentz series of this one is itself. That means z minus 1 I have been written over here. Then we have to find out the Lorentz series or the so-called Taylor series of 1 by z minus 1 about z0 equal to 0. Got it? Now we have to find out ls of 1 by z minus 1 about z0 equal to 0. For that, first we have to draw the figure. I told that always the figure is most important. Here I am drawing by hand, but I suggest that you have to use scale pencil and rounder 1, 2, 3, minus 1, minus 2, minus 3, like this. So here 1, 2, 3, minus 1, minus 2, minus 3. This is your 0. Okay, about 0 we have to find out. So this 0 is your z0. If this function is going to spread from this point 0, then it will interact with its singular point. Here for this case, here for this 1 by z minus 1, the singular point equal to the so-called z dash is your 1. So where is the 1? This is the 1. So this point is your z dash. So if the function is going to spread, then it will interact with the 1 and stop its spreading. So this is the region in which we have to find out the Lorentz series of this function 1 by z plus 1. So for that, if somebody is going to be stand at its z dash and moving from z dash to this into this region, then what is the work? Work is your out to in. Outside you are standing and coming inside, so out to in. So this is the situation for out to in. See, this out to in I written over here for your reference. No need to write in your exam. Directly you have to write that 1 by z minus 1 will be equal to 1 by z dash. For out to in your z dash minus z0 minus z minus z0, right? Okay, will be equal to 1 by here z dash is how much? Z dash for this case is your 1. Just write 1 minus z0 is your 1, sorry 0, z0 is your 0. Okay, minus z minus z0 is 0. Okay, so here we have to compare with this one with our original function 1 minus 0 minus z. That means it will be 1 by 1 minus z, but we have z minus 1. For that, to equalize both, we have to multiply minus. Okay, so that implies 1 by z minus 1 we found minus of 1 minus z. I told that you should not remove any bracket, but as it is 0, we can remove. Here also we can remove. So we found 1 minus z, and the first term is 1 taken common outside taken common from these two terms, then 1 we can get 1 minus z itself. So here minus 1 by 1 minus z is nothing but n equal 0 to infinity z to the power n. So Lorentz series of 1 by z minus 1 about z0 equal to 0 or about 0, we found this one. Okay, so therefore the Lorentz series of 1 by z into z minus 1 will be equal to how much? Already 1 by z we have been written over here. So 1 by z whole into this much, that is your minus 1 summation over n equal to 0 to infinity z to the power n. Okay, this is minus 1 means simple minus. So this is the required Lorentz series about z equal to 0 of this function. Now we are going to go for Lorentz series, finding the Lorentz series about another singular point. So another singular point is your z equal to 1. Okay, so about z equal to 1, another singular point we are going to consider. So for this, first you just consider the original function. What is the original function? Original function is your 1 by z into z minus 1. So this, first write this one, 1 by z into 1 by z minus 1. So here clearly it can be observed that for this one 1 by z minus 1, the singular point is 1. So what will the Lorentz series of 1 by z minus 1 about its singular point itself? So first you write 1 by z minus 1. Okay, kam khatam. Now we have to find out the Lorentz series of ls or ts of of 1 by z about z0 equal to 1. Okay, after that you have to just draw the figure, then your work will be over. Draw the figure, most important, drawing the figure. So this is g1, 1, 2, 3 and so on, -1, -2, -3 and so on. Okay, okay. So z0 means here this is the z0 equal to 1, right? Z0 equal to 1 given, but about this point we have to find out the Lorentz series. Z0 equal to 1. So here now 1 by z is going to be spread from this point. It is spreaded. When it will interact, it's a singular point. Its a singular point is your 0 here. Here is the singular point of this function z dash. Okay, this is 0. It will stop. It will stop. That means if somebody will be stand on this singular point and moving into this region, that means case is your out to in. Okay, out to in. Now now you just write here separately. We have to find out the ls of 1 by z. Ls of 1 by z, z0 equal to 1. Here for this case, the singular point or the so-called z dash is your 0 and case is your out to in case. Out to in case means 1 by z will be equal to 1 by z dash minus z0 minus z minus z0, right? Okay, 1 by z dash is your 0 minus z0 is your 1 minus z minus z0 is your 1. Compare with this one with this. Here -1 plus 1 got cancelled, but minus z we found. But originally is your 1 by z plus 1 by z. For that we multiplied minus. Now it is both are equalized. So that implies 1 by z will be equal to here -1 by -1 minus z minus 1. I told that you should not remove this bracket, but first term take common from these two terms. So -1 is there, -1 common from these two terms. We found 1 plus z minus 1. Minus got cancelled. We found 1 by 1 plus z minus 1. So 1 by 1 plus z minus 1, that is in the form of what? 1 by 1 plus x. So what will be the series? What will the series? This one will be equal to summation over n equal to 0 to infinity minus 1 to the power n z minus 1 to the power n, because z minus 1 will be always less than 1 in this region. Okay, so hence Lorentz series of the function of the given function, that is your 1 by z into z minus 1 will be equal to, already 1 by z minus 1 is written over here. 1 by z minus 1. Okay, then Lorentz series of 1 by z about z0 equal to 1, we found this one. We have to just write here n equal to 0 to infinity minus 1 to the power n z minus 1 to the power n. Got it? Like this you have to do. Now we are going to go for another question number 16. Question number 16. So here the question is that find the Lorentz series of 1 minus cos z by zq about z equal to 0. So given function is your what? Fz equal to 1 minus cos z by zq. This can be written as 1 by zq into 1 minus cos z. So here about z equal to 0, we have to find out the Lorentz series. Consider this function 1 by zq and 1 minus cos z. Among these two functions, whose singular point is your z equal to 0? This one. 1 by zq has the singular point is your z equal to 0. So ls of 1 by zq into 1 minus cos z will be equal to how much? Ls of 1 by zq about its singular point will be the same, 1 by zq. I have been written. Then ls or ts of 1 minus cos z about z0 equal to 0. Okay, so now what will the series? 1 by zq, here I have been written here 1 minus cos z Taylor series about z0 equal to 0 means this is the simple expansion, that is your already we done. Maybe you can refer your previous note or previous video. Cos z about z0 equal to 0, we already found the Taylor series. What is that? 1 minus z square by 2 factorial. See, this it will be z minus z0 square by 2 factorial. Here z0 is your 0, so no need to write the 0. then plus z to the power 4 by 4 factorial, then minus z to the 6 by 6 factorial, then plus so on. Okay. So in the exam, if you are going to leave this much, also you can get the mark if it is 2 mark. But you just simplify it. It will be 1 by zq. Here 1 minus 1. This 1 minus 1 will be 0. This minus is going to be multiplied with all the terms. That means this will be plus z square by 2 factorial, then minus z to the power 4 by 4 factorial, then plus z to the 6 by 6 factorial, then minus, and so on. Then again 1 by zq, if it is multiplied, then we can found this will be 1 by 2 factorial into 1 by z minus z by 4 factorial, then plus z square by 6 factorial minus so on. So this is our required Lorentz series of this given function about z equal to 0. Here you can see, if you want this one in the summation format, it can be written as like this: summation over n equal to 2 to infinity minus 1 to the power n into z to the power 2n minus 5 whole divided by 2n minus 2 factorial. So I suggest तो इतने झंझट में मत 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 घुसो, तो इतना ही लिख दो. Here you can verify. If I am going to put n equal to 2, here minus 1 to the 2 means 1. Here 2 means 4 minus 2. 2 factorial it is there. If I put 2 over here, the 2 means 4 minus 5. That means z to the minus 1 means 1 by z. Okay, first term you got. N equal to 3 you just put. So for the second term, this one. Second term, no. N equal to 3 means minus 1 will become minus came. 3 means 6 minus 2, 4 factorial. 6 minus 5 z. N equal to 3 if you are going to put, you can get this term. Okay. If you want, you can write in this summation format also. Now we are going to go for the next question. Is that? So this is the question: sin z square by z to the 4 about z equal to 0. So given question, given function is your fz equal to sin z square by z to the 4 can be written as 1 by z to the 4 into sin z square. Here z0 is the singular point of this function. If I will put z0 equal to 0, so this cannot be defined or not analytic, but here this will be 0. If I will put 0, sin 0 means can be analytic. So z equal to 0 is the singular point for this function. Okay, so Lorentz series ls of 1 by z0 into sin z square about z0 equal to 0 will be how much? The Lorentz series of this one about z0 equal to 0. Here this one means 1 by z to the 4. 1 by z to the 4 singular point is itself is your 0. So Lorentz series of this one by z to the 4 about its singular point is itself z to the 4. I have been written. Okay, now into ls or ts of sin z square about z0 equal to 0. So sin z square means this the simple expansion of sin z. Here sin z expansion we know, sin z expansion we know what, that is your z by 1 factorial minus z cube by 3 factorial, then plus z to the 5 by 5 factorial, and so on. This is the sin z expansion or the so-called Taylor series of sin z. This is the Taylor series of sin z about what? About z0 equal to 0. We know that. We know when we discuss the Taylor series. But here instead of z square is there. So here instead of z, it will be z square. We have to write. Okay. So that implies, so will be equal to Lorentz series of this one will be equal to what we have to write, 1 by z to the 4 whole into, here instead of z square, that means what? It will be z square by 1 factorial minus, instead of z we have to write z square whole cube by 3 factorial, right? Then plus z square to the power 5 by 5 factorial, then minus, and so on. Okay, so this is the Lorentz series of this given function about z equal to 0. If you want, you just simplify it. If I am going to simplify, or you just keep it this much only. This is the required Lorentz series of this one. If you want to write, it's a this this series in the summation format, it will be how much? 1 by z to the 4 whole into summation over n equal to 1 to infinity minus 1 to the power minus 1 to the power n minus 1 into z to the power 4n minus 2 whole divided by 2n minus 1 factorial, right? So if you want, you can match. Consider n equal to 1. If I will put n equal to 1 over here, the minus 1 to the 0. That means plus, okay? N equal to 1. 1 means 2 minus 1. 1 factorial I got. Here n equal to 1 means 4 minus 2. Z to the 2. Got it? Now n equal to 2. If I am going to put 2 minus 1, 1. That means minus 1 to the 1 means minus came. 2. 2 into 2. 4 minus 1. 3 factorial. Then 2 into 4. 8. 8 minus 2 is your 6. So z to the 6 can be written as z square to the power 3. Right? If I'm going to put n equal to 3, that means minus 1 to the 3 minus 1 means 2. That means minus 1 to the 2 means plus. 3 means 6 minus 1, 5 factorial. Here 3 means what? 12. 3, 4 into 3, 12 minus 2, 10, z to the 10. Here you can say z to the 2 to the power 5 means 10. So this is the summation format Lorentz series of this function about z equal to 0. Okay. So this is the all about the revision and some basic questions on Lorentz series. Okay. So here we are going to stop our discussion. We are going to discuss in our next class. We are going to discuss this one: poles and branch points, order of the singularity, branch chord. Already we have been discussed. That means different type of poles. What are the branch point, order of the singularity, that we are going to discuss in our next class, and corresponding numericals also we are going to discuss. Okay. Here I forgot one thing, that here most important that you have to remember. Here you can see, suppose I am going to consider question number 5. Carefully you have to watch question number 5 or 4. You just watch question number 4. In the question number 4, it is asked that find out the Lorentz series of 1 by 5 minus z about z equal to 7. So here z equal to 7 is not the singular point. In the figure, z equal to 7 is here. Okay, and we have to find out the Lorentz series about this Lorentz series of this function about this point, and its singular point is at 5. So if the function will spread from here, it will interact with the singular point, this one, and in this region what will be its the so-called Lorentz series or Taylor series? We found this one. Okay, we found this one. But here you should remember that here we considered this inner region. Also we have to consider the outer region. If this question asks that only single question, it is asked that we have to find out 1 by 5 minus z about z equals 7, then we have to also consider the outer region. Okay, for outer region, what will be here for outer region? For outer region, what will the Lorentz series? That means outer region means here you are standing, no, at the z dash you are standing here, you are moving from this point to outside, means in to out. In to out situation. In to out situation means 1 by 5 minus z will be written in this form as z minus z0 minus z dash minus z0, right? So here 1 by z minus z0 is given as 7 minus z dash is your 5. Sorry, z dash is your yes, z dash is your 5 minus z0 is your 7. Okay, now you just compare this and this one with this one. If I will match, here you can see z minus 7, here 5 minus 7 means minus 2 minus plus 2 plus 2, and here minus 7. That means z minus 5 we can get, but the initial function is 1 by 5 minus z, so I have to multiply minus. Okay, so here 1 by 5 minus z, Lorentz series of 1 by 5 minus z will be equal to minus 1 divided by, here first term is your what? Z minus 7. First you write z minus 7 minus this one is your what? How much? This one is your minus 2, and here minus is there, so it will plus 2. So first term, this bracket term in which z is there taken outside, z minus 7 taken outside, means we found 1 plus 2 by z minus 7. Okay, now the Lorentz series will be how much? Minus 1 by z minus 7 is there, and this will be summation over n equal to 0 to infinity. Here 1 plus 2 by z minus 7 is there, 2 by plus is there, so minus 1 to the power n into 2 by z minus 7 to the power n. So this will be the Lorentz series for the outer region. Okay, likewise for this question also you have to do in the exam. That means about z0 equals 7, which is not the singular point, means we have to consider inner region and outer region. Inner region I already explained, outer region you have to do. How we have to do, I explained. Here also same. Here inner region, for the inner region what is the Lorentz series I have been already discussed, and but in exam also you have to consider the outer region. So whenever you are writing the note, no, at that time I forgot to say that you have to also do the Lorentz series for the outer region, but you have to do inner note. Okay, here here is the space will there, or you can paste another page here. Okay, okay, so this is all about this class, that we revised the Lorentz series and corresponding numericals, and finally also we have been discussed some basic questions. Okay, hopefully this video series belongs to Lorentz series will help you a lot in for your exam. Thank you so much for watching this video. I told in our next class we are going to discuss this one. For that you have to ready. Okay, branch poles, that means different type of singular points. Here poles means different, what type of, how many types of poles, order of the poles, order of the singularities, different type of name of the different type of singular points and branch points. Thank you so much for watching this video. Thank you.